We're standing on the grounds of the National Astronomical Observatory of the Department of Astronomy at the University of Chile, perched atop Cerro Calán hill in the Las Condes commune of Santiago. Here, we're meeting with Valeria Olivares, a young scientist and astrophysicist. Valeria specializes in unraveling the complex astrophysical processes that unfold in the centers of galaxies. She was a NASA postdoctoral program fellow at NASA's Ames Research Center and coordinator of several projects studying the feedback mechanisms in active galactic nuclei. Today, we're going to talk about black holes, some of the most mysterious objects in the universe. We'll also try to find out what exactly is at the center of our galaxy and whether there is really a black hole there. Greetings, dear friends. It is a great honor for me to introduce Dr. Valeria Olivares. She is an astrophysicist and researcher, PhD, Faculty of Physics at the University of Santiago de Chile. She is a young scientist, passionate about her work. Welcome, Valeria. We are very glad to meet you.
Good afternoon, Paulina. Thank you very much for the invitation.
We're very glad to be here and have the chance to talk with you. Let's start with our first question. Valeria, what motivated you to study the processes taking place in the centers of galaxies? And what aspects of astrophysics inspire you the most?
Well, I became fascinated with studying what happens in the centers of galaxies because I'm interested in the process of galaxy formation and evolution. What happens inside a galaxy has a major impact on how the galaxy evolves and its properties. There are what we call active galaxies, which have a supermassive black hole at their center. These black holes accrete, absorb matter. And as they accrete matter, some of them produce what we call jets, while others generate high radiation pressure. Both of these phenomena can significantly influence the properties of galaxies. That's why I'm so interested in studying the processes happening in the center of a galaxy. One of the questions I'm trying to understand is how these jets and the radiation pressure, that is the impact of a supermassive black hole inside a galaxy, affect star formation, and how this, in turn, affects the properties of the galaxies themselves.
How can we determine if there really are black holes at the centers of galaxies? And how accurate is this idea?
One of the ways we can learn that there is a black hole at the center of galaxies is by observing the dynamics of the stars that are located around the galaxy. We can see clusters of stars in the center of our galaxy. We have observations gathered over many years, and we can track the orbital periods of the stars that are very close to the galactic core. The speeds of these stars are extremely high. We have been measuring the orbits and periods of these stars for many years, so we know their trajectories very precisely. And one of the things these observations show is that there is an object that does not emit light, that we cannot see with our existing telescopes, yet it exerts a significant influence on the motion of these stars. This means there is a very, very massive body that we can't see. This is one of the pieces of evidence supporting the existence of a black hole. And the direct evidence is the observation of the black hole's shadow, matter that is orbiting the black hole, which we captured with the Horizon telescope a couple of years ago. That image truly became the direct evidence that supermassive black holes do exist inside galaxies.
So, can we say that thanks to the discovery made with this telescope, we can mark a clear before and after in the study of black holes?
Yes, absolutely. This has become direct evidence that supermassive black holes are located at the centers of galaxies, and not just in our own. We have also observed them in the elliptical galaxy M87, which is relatively close to us. There, we detected another supermassive black hole too, and in the image, we can also see the matter that surrounds this supermassive black hole.
And that raises the question, what's the difference between black holes at the centers of galaxies and stellar black holes?
There are two main differences with stellar black holes. The first difference is their mass, and the second difference is in how they formed. For example, it is believed that stellar black holes are formed when a star collapses and explodes as a supernova, and the core that remains inside collapses to form a stellar black hole. And these stellar black holes are much less massive. Their mass ranges from about 2 to several tens of times the mass of the Sun. In contrast, supermassive black holes found inside galaxies are much more massive. For instance, they can reach masses from 10 to the 6th power, that is, from 1 million to several billion solar masses. These are extremely massive black holes. The difference lies in how did these cores, these supermassive black holes, actually form? In fact, we still don't fully understand how they formed.
I'd like to dive deeper into this topic now. How long have black holes at the centers of galaxies existed? Have they remained in their current form since they first formed? And why hasn't such a supermassive black hole swallowed the entire galaxy over the course of thousands and millions of years?
To better understand this question, we need to delve into how supermassive black holes in galaxies formed. One theory suggests that they emerged shortly after the Big Bang, the moment of the universe's creation, when clouds of gas existed, composed mostly of hydrogen, but also containing some helium. These clouds are known as primordial clouds, and it is believed that they began to radiate energy, lose it, and consequently cool down and become denser. At some point, these clouds collapsed, forming smaller black holes, called primordial black holes. Over time, these primordial black holes merged with each other, creating supermassive black holes, much larger, much more massive. This is how the very black holes we observe in galaxies today are thought to have formed. Now, as for the other question, are the black holes that existed in the past the same as the ones we observe today? Well, the answer is both yes and no. The basic structure of black holes has remained the same, but their properties have changed over time and differ from what they were in the past. For example, they can merge with one another, so the mass of these black holes can increase, both through mergers and by accreting, swallowing, surrounding matter such as gas and dust. Additionally, the merging of different supermassive black holes can change the nature of their rotation, what is known as spin. There are also other processes, as I mentioned earlier, through which some galactic supermassive black holes continue to accumulate matter. The growth of this matter can lead to the formation of what are known as active galactic nuclei, AGN. And as their properties evolve, they can develop what's called an accretion disk, a structure where the accreting matter becomes extremely hot and orbits the black hole. There are many such processes, and one of the important ones is the production of these jets. So, the black holes we observe in the past have clearly changed their properties over the course of their lifetimes, and they are quite different from what they were when they first formed.
Of course I understand. Then the question arises, why hasn't a supermassive black hole of this type consumed the entire galaxy, say, over billions of years?
Of course, that's a very good and truly interesting question. And the answer is that galaxies are very large structures, and the stars within them are extremely far apart, so there's quite a lot of empty space around them. A more specific answer is that the gravitational pull of a black hole only significantly affects the area close to it. It doesn't have an influence on what happens around it at larger distances. In other words, gravitational attraction, the force of gravity, decreases with distance. The gravitational force of a black hole diminishes with distance, so its sphere of influence is relatively small compared to the vast scales and distances found within galaxies. Black holes do not significantly influence what happens beyond the galactic core. Outside the galactic nucleus, it's the galaxy itself that dominates. Another important aspect that helps answer this question is that some supermassive black holes at the centers of galaxies have active galactic nuclei that produce jets. These jets expel the surrounding gas, thereby preventing it from being accreted, absorbed by the black hole. This, in turn, prevents the black hole from growing in mass. If its mass increases, its gravitational field would be stronger. Thus, this process also acts as a limiting factor, keeping the gravitational force from becoming too large and from having an overly broad impact on the galactic core.
In the Spanish-language translation of the article, X-ray surface brightness correlation for filaments in cooling flow clusters, it is stated that active galactic nuclei create bubbles in the surrounding hot gas and influence the formation of multiphase filaments in galaxy clusters, indicating the presence of both hot and cold flows. Could you explain the concept of these types of two flows in galactic nuclei?
Yes. I think the best way to understand what hot and cold flows are is by looking at galaxy clusters. These are the most massive gravitationally bound structures in the universe. They consist of many galaxies, from a few thousand to hundreds of thousands of galaxies, all held together by gravity. At the center of these clusters is a special galaxy known as the brightest cluster galaxy. It is the most luminous, massive, and active galaxy, and it hosts a supermassive black hole in an active state. So, it is capable of creating a feedback loop by producing jets. These jets create the bubbles you mentioned, which then interact with the surrounding gas known as the intracluster medium. It's a very hot gas, with temperatures reaching up to 10 million degrees Celsius. This interaction with the surrounding gas creates streams or filaments that I refer to as multiphase filaments, which we observe in a cold state. However, we have also found that they can be very hot. This is how they form. Through the interaction of the jets with the surrounding gas. Then, these cold filaments, it is believed that they can collapse upon themselves because they are quite clumpy. There are these molecular clouds, dense, cold clouds, that are thought to collapse and form stars, and also fall toward the galactic center, feeding the supermassive black hole. In feeding it, this can again trigger the formation of more jets, which then interact with the surrounding gas and form new filaments, and so on. This is called the supermassive black hole feedback loop, or cycle. Galaxy clusters contain extremely hot gas. It's a diffuse gas that we can observe in X-rays, because it is so hot that it naturally emits at these wavelengths. So, we can observe them using satellites in space, Meanwhile, the cold flows in this concept correspond to these filamentary structures, which are not only cold, but can also be observed in warm gas. So they're multiphase. And this cold gas can have a temperature of less than 100 Kelvin. So how do these structures form, you might ask? Well, that's what I've been working on for nearly my entire scientific career. How do they form? Apparently, the supermassive black hole that is active generates these jets, or radio jets, that I mentioned earlier. They interact with the hot gas and create turbulence. By interacting with the hot gas, they promote its condensation into these colder, filamentary structures. These structures are very, very elongated and have quite a peculiar appearance. They are very beautiful.
I have another question. Do magnetic fields play any role in the formation of these flows? And if so, what mechanisms, in your opinion, form these magnetic structures?
Basically, we believe that magnetic fields help maintain the elongated, filamentary structure of these filaments. More importantly, they prevent these filaments, which contain very dense and very cold molecular clouds, from collapsing and forming a large number of stars. So they help to prevent excessive star formation. So they help stabilize these flows and play an important role in star formation. Essentially, they create a pressure that counteracts the gravitational force of this cloud. Thus, the magnetic pressure they generate prevents these clouds from collapsing and forming a large number of stars. It is one of the most significant effects they can have on these flows.
Wonderful. All the information you're sharing is incredibly interesting, and I can't help but ask, what kind of data and tools, I mean telescopes or simulations, do you use in your research?
I try to use all the telescopes available to me. Every observation, every telescope, every wavelength can provide a new clue, a new key that might help solve the bigger puzzle. For example, I enjoy using telescopes that observe in X-rays. I mean space-based satellites, such as the Chandra satellite, which gives us information about hot gas. I also use data from the Very Large Telescope, VLT, located in northern Chile. I specifically use this telescope to study colder filaments, to examine their kinematics, various properties, morphology, and so on. These are optical observations. I also use data from the ALMA interferometer telescope, which operates in the radio and sub-millimeter range and is also located in northern Chile, in the Atacama Desert. This telescope is unique because it allows us to study molecular clouds, which are the main component in star formation, as well as the fuel for supermassive black holes located at the centers of galaxies.
And what scientific discoveries, for instance, could change our understanding of black holes and galactic centers?
I think that direct detection of gravitational waves produced by the mergers of supermassive black holes in galaxies could help us better understand the dynamics of galaxies and how these processes influence their formation and evolution. Another discovery that, in my view, would be particularly interesting concerns dark matter, which, as we know, is one of the main components of galaxies and contributes significantly to their mass. In my view, the discovery of dark matter would play a crucial role in understanding the evolution of galaxies. Dark matter is an essential component of galaxies, contributing significantly to their total mass. But it remains deeply mysterious, as we can't observe it the way we do visible matter. It doesn't emit light. That's why I believe that detecting dark matter, whether in laboratories or through astronomical observations, could provide us with many clues about its origin and the influence it may have. It would help us understand how galaxies formed and what role dark matter might play in their evolution.
What is the purpose of black holes? After all, technically they could destroy entire galaxies, or is that not true?
No, because it's a complex question. From the perspective of my research, I'd say that black holes actually help form new galaxies. They also play a role in star formation, and stars are essential for the formation of planets. So in a certain sense, they contribute to the creation of smaller structures.
So, on the one hand, black holes are kind of helping to create new galaxies, new stars, and everything that's needed for the life of another galaxy?
Of course, they help alter the properties of galaxies. That's how fundamental their role is. The thing is, black holes will never consume an entire galaxy, because their influence is limited to its center. They don't affect what's happening beyond the core of the galaxy. And these passive galaxies, as a rule, have smaller black holes, so their impact is even more limited.
Valeria, you also teach at a university. Based on your observations, what most motivates your students to study such phenomena?
I think students are really drawn to exploring the structure of black holes. Why are they arranged that way? Why can't we observe them directly? What evidence do we actually have that they exist? I believe these questions are of keen interest, not only among students but in the wider public as well. I think what fascinates me most about black holes is what happens in active black holes, in active galactic nuclei, AGN, and the tremendous impact they have on galaxies. That's what truly impresses me and inspires me to keep researching this topic. I'm particularly interested in the role black holes play in star formation. We still don't know for certain whether they help trigger the birth of new stars or actually hinder that process. And it's exactly this question that motivates me to continue exploring this field. The desire to better understand the role of black holes and how they influence the formation and evolution of galaxies.
That's just amazing. Thank you for this interview. It's very important information, and it can especially support the research being done by the Kaleidoscope of Facts team on the online platform Alatra TV. Thank you so much, Valeria, for taking the time to speak with us.
Thank you very much for inviting me to this interview.